Sahi from Rutgers, and he will tell us about metaplectic representations of Hecke algebras.
Well, thank you so much. This is, for me, it's the first time giving such a talk, so probably I'll make all kinds of mistakes. One of the mistakes I kind of realize I'm making already is that what I'm showing, the slides are on a different screen. So I don't know, how does it work? Do you see my slides or do you see me as well?
We see both you and the slides.
You see both of us, yes? Yes, so, okay, but so the camera is maybe on the wrong side, so I'm looking, I mean, I should be looking at the camera when I'm talking, so otherwise I'm looking off, staring off onto the side. Okay, well, I'll try not to share too much on the side. I'll just kind of talk. Okay, so, well, I'm very happy to be speaking in this seminar, and thank you for the invitation. Okay, so this is joint work with Jasper Stockman and at Amsterdam, and Vidya Venkateswaran, who's at CCR and Princeton. And I think Vidya is joining us by in the conference, but I'm not sure if Jasper has a chance. It's sort of a little bit later in Holland. So yes, so I will try to explain what we have done in this. So this is some work we did, but about a year ago, and it's continuing. So I will be speaking mostly about the part that's already on the archive, but I will also talk a little bit about work that's in progress, which we hope will be on the archive pretty soon. Okay, so let me just start with some background. So I have some root system phi, and alpha i's are some choice of simple roots. W is the Weyl group, and P is the weight lattice. Okay, I look at the group algebra of P, which I write as Cx bracket P, and I formally expand by these elements x to the lambda, where lambda is in P. And this is some algebra, and I pass to the fraction field, which I call C sub x parentheses P. So that's the fraction field. Now, the Weyl group acts on P, therefore I get some representation on the group algebra and also on the field of fractions, and I will call this the reflection representation, pi. This is a reflection representation of W. Okay, so now the point is that this pi is in fact the first in some family of representations, which I call pi 1, pi 2, pi 3, and so on. So I would like to explain this point. This pi sub n in general depends on some bilinear form on the weight lattice, and also some additional parameters. So I call them v and g1 sub integer part of n over 2. So n equals 1, there's no parameters, but for general n, you have roughly n over 2 parameters in this representation. And this representation was defined by Chinta and Gunnells, and it's motivated by the work of Kazhdan-Patterson, where this essentially appears for GLN in their work on metaplectic forms. And the general thing arises in number theory, more precisely in the subject of Weyl group multiple Dirichlet series. And in the application to these WNDs, these GIs, these extra parameters, are certain Gauss sums. Let's see if we can just hit enter to proceed. Okay, so this is these are the representations I want to talk about. So let me explain how this representation is defined. So it involves some deformation factor, but let me set that up. So as I said, let's choose a W invariant symmetric form on the weight lattice V. I'm going to assume that this form is the associated quadratic form, which is Q lambda, which is 1/2 B lambda. Lambda is integer valued. And moreover, I want to simplify things. I want to make the further assumption that the possible values of Q on the roots are co-prime to this integer n. If it's not the case, one can still do it. It's just the formulas become more complicated. So this is a mild assumption because n just avoids finitely many primes. Okay. Then I let P sub n to be the sublattice, which is defined by, which is all those lambdas whose pairing with the roots are in 0 mod n. And now the group algebra, sorry, the fraction field that I want to study, Cx of P. So it's spanned by elements which are in the fraction field of Pn times some monomials, x to the lambda in P. So basically, if you have some expression, you can multiply by some factor to make sure that the denominator lies in this Pn. So then you can write a general element as a combination of such things in the fraction field. Okay. The pi n action for the simple reflection, so if I look at the simple reflection, S alpha I, it's related to the usual action by some deformation factor. On deformation factor, you choose some element fx lambda. How does pi n of Si act on this fx lambda? Well, let me just divide out by the action of pi and tell you what is the new thing. I call this some gamma I n of lambda. So it's some deformation factor. And it takes values, I mean, it's something, it's some function from P mod Pn to rational functions on P. Okay, so now I will explain what's the deformation factor. If you have any questions at any point, if I'm going too fast, please stop me and ask. So let me give an explicit formula for this deformation factor. So first, I will write Rn of bracket A to be the remainder of A mod n. So it's something from 0 to n minus 1. Now I can actually extend this in some completely natural way to rational numbers A mod B with the property that the GCD of n and B is 1. Because I just take the inverse of B. So it's something 1 inside here. So I would really have this Rn as a map from such rational numbers to this residue classes. Okay. Now, as I said before, we need certain parameters. So I fix a parameter V, and then I also fix some GJs, which are really, they're periodic mod n. So really Z mod n Z. And they satisfy the following property. So G0 is -1, that's a natural normalization. Otherwise, Gj and G minus J, they multiply together to V inverse. So V inverse is this other auxiliary parameter. So, essentially you have n over 2 of these GJs, which is what I was talking about before, but this is a more precise way to fix the parameters. Okay. So here is the deformation factor. It's kind of complicated. So gamma I and lambda, it's 1. Okay, so yeah. Okay, this is it. Okay, so it involves lots of things. It involves this Rn. Can you see my cursor also?
Yes, we can. Yeah.
Okay, good. So here is this Rn, and the Q lambda is coprime. That's an assumption that it's coprime to n. So this Rn, this is some well-defined number between here and there, and this is what's in the exponent here. And then here's some ratio of the g's. I could use this relation to rewrite it as g sub something if I wanted. So the ratio of the g's is really just some other g up to v. And there it is. So it's some complicated thing involving many parameters in these conditions. Okay, so the theorem of Chinta and Gunnells says that this formula now defines a representation of W on the field of fractions of the weight lattice. Field of fractions of the group algebra of the weight lattice. And so, okay, you have to see that it's well defined because, as I said, it acts on how it acts in some place, and you have to check that it's invariant in the linear combinations. That's sort of easy-ish. Then you also have to check that the square, these guys, the sigma, the SI is in the action square to 1. This is kind of messy, but manageable. The hard thing is to check the braid relations to see that you actually get a representation of the Weyl group with all of this mess going on. So the original proof by Chinta and Gunnells actually involves computer check of these braid relations, and it's like too much to write down even. So therefore it's desirable to have a more conceptual proof, and this was already pointed by Chinta and Gunnells. This was already noted by Chinta and Gunnells that it's not to have such a proof. So that's what we did. It's in this in the archive, in this preprint. So we provide such an argument, conceptual argument. This argument involves the affine Weyl group. Let's call it curly W, which is the semi-direct product of W and P. And it's Hecke algebra. So really you need the Hecke algebra. And the point is that the Hecke algebra, the affine Weyl group, is actually isomorphic to the group algebra after some localization, which I will explain. And so what we do is we actually construct a representation of the affine Hecke algebra, which we call curly pi sub n. And then we obtain pi n by localization. Okay. So this localization procedure is sometimes also called Baxterization. This allows you to construct a representation of the Weyl group from a representation of the Hecke algebra. It basically involves this localized isomorphism. Okay, so that's the idea that maybe the representation of the affine Hecke algebra will be easier to understand. And somehow part of this was motivated by work of Chinta, Gunnells, and Pushkas, who were sort of going in the other direction, that they were constructing some Hecke algebra representation, starting by trying to deform the Weyl group, the Chinta-Gunnells Weyl group action. But it's actually, from our point of view, it's kind of easier to. So in their construction of the Hecke algebra representation, they used the fact that you had a representation of the Weyl group to begin with. And so this involved some checking. So our point is that one can actually construct the Hecke algebra representation directly, and then going in this direction is localization. So I want to explain what is this Hecke algebra representation that we have. Well, I'll do that in a moment. So I want to first briefly talk about, so we call this the metaplectic representation. And the point is that it leads to some interesting polynomials. So let me explain this. So so this is in work in progress with Jasper and Vidya. We extend this curly pi n to the double affine Hecke algebra. So I mean, it came to life as a representation of the affine Hecke algebra for localization, but it in fact extends to the double affine Hecke algebra. The extension of curly pi 1 is the usual quote unquote polynomial representation studied by lots of people. And the well-known Macdonald polynomials, they arise naturally in the context of this polynomial representation of the DAHA. So it turns out that these metaplectic representations lead to a natural family of metaplectic polynomials. It's E lambda upper n, which will now depend on a bunch of extra parameters that went in. So the G's, the V is already present. It's basically some Hecke parameter, but with these extra G parameters, which in interesting applications are Gaussians. And these polynomials, E lambda upper n, appear to share many features in common with the usual Macdonald polynomials. And it's interesting to understand precisely which properties generalize. So my student Kazhdan Sahi at Rutgers has been looking at these polynomials for the GLN group, and he has some very interesting results. That's in the preprint, but hopefully it'll be out shortly, which understands, for example, the alcove walk type model for these, which gives some sort of alcove walk type model for these representations, for these polynomials. Okay, so let me explain our construction. So I start with the finite Hecke algebra, H. So this has generators Ti, T1 through Tr, where R is the rank. I don't want to say N is the rank because N is some metaplectic parameter. Okay, so its rank is R. I'm not sure I'll need it explicitly, but N has nothing to do with the rank. Okay, so it has some generators Ti, and they satisfy the braid relations. And I want to impose the quadratic relations Ti minus K times Ti plus K inverse, where K is the square root of this parameter V that was mentioned before. Very good. So I want to study some simple-minded reflection representation of the Hecke algebra. So it's pretty simple-minded, but so you can check that this is a representation. So I'm not sure, kind of before we did this, whether this was kind of commonly looked at, but it's rather a simple. It's given by rather simple formulas that you see over here, and it's rather straightforward to check that this is a representation of the finite Hecke algebra. Right? Because the formulas are not very complicated. So this is how it acts. The matrices of these elementary generators are size 1 or 2 or something. So we can check together representation. All right, so now, depending on this n, I look at an inflated alcove. So it's some finite set. So it's all lambda in P such that lambda paired with alpha check is less than or equal to n for all alpha in the root. because I'm imposing some condition both on alpha and minus alpha, this is some bounded region. Phi is all the roots. Right? So it's a condition in the absolute value of the inner product. So it's some finite set. And this set is stable under the Weyl group W, under the action of the Weyl group W. So what this means is that I can take the reflection representation U, and I have this finite dimensional piece in there, which is an H submodulo. Because the fact that C is stable under W, and you see how the generators of the finite Hecke algebra act. So on this space U sub C, I get finite dimensional representation of the affine Hecke algebra. So this is some seed for starting. All right. So now let me look at the inflated root system, phi upper n, which is just all n times alpha for alpha in the root. So this is a root system, clearly. And its weight lattice is this p sub n, p upper n, that we discussed before. So let's take the group algebra of this p sub n that I'm going to call that C sub capital Y. And it is spanned by formal exponentials y to the mu, where now mu ranges in Pn in this sublattice Pn. And I want to look at the affine Hecke algebra. So more precisely, I want to look at this affine Hecke algebra. I should really call it H upper n, but I'm going to suppress the H. So this is generated by the finite Hecke algebra and the group algebra of this Pn lattice. And here is the relation. So the SIs kind of don't care whether you're looking at a root or multiple of a root. But here I have, in the denominator, I have n. But this gives a representation. I mean, this is this defines this affine Hecke algebra. It's generated by H and Cy, and this you impose this relation. Okay, and now I can construct an induced representation of this affine Hecke algebra. So I take that UC, which was a representation of H, and I induce it to the affine Hecke algebra, curly H. And it's going to be realized on the space NC, which is the tensor product of UC with CY. This is more or less a consequence of the PBW theorem for the affine Hecke algebra. That just as a vector space, it's a tensor product of H. So you look at the multiplication map of H tensor CY to the affine Hecke algebra, and this multiplication map is an isomorphism. So therefore, this induced representation has a natural realization on the space NC, which is UC tensor CY. Okay. All right, so now let me explain what's the metaplectic representation. So yes, so I just want to recall what are the parameters. So V is K squared, K was some square root of V. And Gj were these parameters satisfying this condition. Okay, so now I want to define, I used this gamma j before, and this gamma j has nothing to do with that. I should have used some other letter. I just, for this deformation factor, I used gamma j. Please forget that. Okay, now this is some new in tech you can redefine that. So this is redefining. Okay, so I will define gamma j to be essentially gj, except I'm cutting it off. So for j bigger than or equal to 1, for j bigger than for positive integers, I define gamma j to be 1. And for negative integers, well, okay, there's two things. It's essentially gj. There's yeah, except you have this factor of k as well. So, but anyway, here's the definition. So these gamma j's are some more convenient way of capturing the same information as the k and the gj's. The gamma j's know parameters just as well. Okay. All right. Now for lambda in this inflated alcove C, I define gamma of lambda to be the product of L over positive roots of gamma sub Q alpha times lambda alpha check. Okay, so this is somewhat complicated, right? Because the formulas look simple, but if you unravel them, there's quite a bit going on. And now I want to define a surjective map from NC, which is where the representation sigma was realized, this induced representation. I want to map it to Cx of P. So in other words, just the group algebra of the weight lattice. So there's all sorts of letters which are being used here to keep the different lattices apart. And I'm using formal exponentials. So here in this space U, I'm writing U sub mu. In this space, I'm writing y to the mu. So this is U sub lambda, y to the mu. And I'm going to map it to x to the lambda plus mu. And the whole point is that I put this factor 1 over gamma lambda in front in this map. So it's some obvious map with some highly non-obvious scaling factor. So this is a definition of this map psi. And it's a surjective map, clearly. And the main result that Vidya and Jasper, Jasper, Vidya, and I proved is that the kernel of this map is stable under sigma. So sigma was this induced representation acting here. And I have a map, a surjective map onto this space. And I can look at the kernel of this map. And the claim is that the kernel is stable under sigma. So what this means is that I get an action of the affine Hecke algebra on this right side, because I realize that the group algebra of P as a quotient of the representation sigma. So this is how we obtain a representation of the affine Hecke algebra on CXP. Right, so let me just kind of recap what we did. So we started with some finite dimensional representation of the affine Hecke algebra, which was some piece inside the reflection representation. And then we induced it to the affine Hecke algebra and then we cleverly constructed a quotient. And one advantage is that at every stage you have a representation, and checking that the kernel is stable, you do not need to check braid relations. This is the whole advantage. You just need to check that it's invariant under the generators. So this is hard, but it's less. I mean, it's more conceptual. There's still some magic because the gammas have some magic in them. But okay, then the checking is kind of an easier check. Okay, so what does this metaplectic representation have to do with the Chinta-Gunnells pi? What does the curly pi have to do with the Chinta-Gunnells pi n? So, okay, so let me explain what is this localization, or this technique of Baxterization. So what we have is that the affine Hecke algebra, which is curly H, if you remember, it's generated by H and C sub Y. So what I mean by the localization is the algebra generated by H and the fraction field of this group algebra C sub Y. Okay, that's the localization of the affine Hecke algebra. And similarly, one can look at the localization of the affine group algebra, let's call it A sub loc. It's generated by the group algebra of the finite Weyl group and the same field of fractions of the group algebra of the lattice. And the theorem, I mean, I shouldn't even call it a theorem, you know, it's sort of a fact, is that you can look at a map from A loc to H loc, which is identity on this Cy of Pn, and which maps the generators Si to these elements of the affine Hecke algebra, or the localized affine Hecke algebra. The reason it's localized is because, you know, there's this ratio that shows up. Then this map extends to an algebra isomorphism between the localized guys. Probably one doesn't have to localize everything. One has to only localize these denominators which show up to get this isomorphism. Okay, anyway, so that's the result. And the fact that this is an algebra isomorphism is essentially equivalent to the relation in the Hecke algebra. So it's not, so this is what I think, I mean, it shouldn't be called a theorem, it should be called sort of an AHA result or something. That's a joke, that's not fine Hecke algebra. Okay. Anyway, so now this metaplectic representation on that we have, so I forgot the n. Okay, but omega is curly pi sub n. It extends uniquely to a localized representation on the quotient field. So we have some representation on the group algebra, then you can localize it to get a representation on the quotient field. And now, via this isomorphism, I have a W action on this space. And this coincides exactly with the Chinta-Gunnells action, that the complicated action that we saw earlier. So this is the main result here. Okay, so all right. So now let me talk about a little bit what's in our forthcoming paper. So we hope to have it up soon, hopefully before the end of the summer. The preprint. So the point is that this curly pi n can be extended to the double affine Hecke algebra. And in fact, one of the things we realized, and which is why it's taking a bit longer to write this paper, is that once you know that you're getting a representation of the double affine Hecke algebra, it becomes much more rigid. So there should be a better way to describe this. That's what we are doing. This is what's causing the delay. But anyway, it's all doable and it's just very beautiful. So once you extend it to the double affine Hecke algebra, then you get an action of these metaplectic versions of Cherednik operators. And that's interesting. So the difference between the affine Hecke algebra and the double affine Hecke algebra consists of a family of commuting operators, which are called Cherednik operators. And if they are acting, then you can look at they act semi-simply, and you can look at their eigenfunctions. And this is how you get Macdonald polynomials. So in this situation, we now have these metaplectic Cherednik operators, and therefore we get polynomials, and we call them E lambda upper n, which generalize the Macdonald polynomials, E lambda. Once you extend it to the double affine Hecke algebra, then this is what you gain. These guys, the E lambda upper n, they specialize to, so where's the word metaplectic in all of this business? So now we come to this explanation. I mean, the word metaplectic already appears in the work of Kazhdan-Patterson, where they talk about metaplectic form. But let me explain this a little bit more over here. So these E lambda n, so they depend on parameters. If you let, if you let the, okay, so if you specialize the parameters, what you recover are certain Whittaker functions. So these are, I should have written a little bit more. So they are Whittaker functions on metaplectic covers of p-adic groups. So that's what I mean by metaplectic covering groups. So they're metaplectic, so n-fold covers of p-adic groups. And then they're Whittaker functions for certain, and they're related to p parts of these Weyl group multiple Dirichlet series. So these Weyl group multiple Dirichlet series, they are global objects associated to metaplectic covers of global groups, so Eisenstein series for covering groups. So it's a huge theory, and there's lots of stuff over there. So, but I'm just explaining that these things are connected to some. They have some sort of they have a life of their own. These specializations, and these E lambdas are generalizing those. Basically, we're putting in another parameter to something. Okay, but in that life, again, the GIs have to be Gauss sums. But okay, never mind. But this is some natural family that has a very interesting and non-trivial specialization related to number theory. Okay, and this, what I just explained, or sort of didn't completely explain, this generalizes the relationship between Whittaker functions and Macdonald polynomials that comes from the Castleman-Schleicher formula for Whittaker functions. Okay. So, all right. So I mean, this is sort of all I want to say, and I want to give some tables of metaplectic polynomials, and I realized that in these tables I use some epsilon. So I'm giving some examples of what metaplectic polynomials look like. So here this epsilon is plus or minus 1, and what it is basically It's when n is even, let's say n is 2m, then the relation on the parameters says that gm squared is 1, the relation that we imposed. So let me just back up briefly. So we have this relation. Well, no. So it says, no, it doesn't say that. So when n is even and j is m, then what I get, g minus m is gm, so I get gm squared is v inverse. Okay, so which means that basically the only thing, additional information, is some plus or minus 1. Okay, so when n is even, so one of these parameters is essentially a sign. So this is the sign epsilon that shows up sometimes here. Okay, so what do the polynomials look like? So these are polynomials for GL3. Okay, so these polynomials look as follows. So for n equals 1, so n is up to 5, and it's in GL3, so it's polynomials in x1, x2, x3, and okay, if I just take 0, then it's always the function 1. When I take 1, 0, 0, so lambda is some composition. That's what's indexing these polynomials. And for 1, 0, 0, it's just x1, so it doesn't look very interesting. Okay, now something happens. So for 0, 1, 0, I get these polynomials. Now I should point out, so for 1, so in Macdonald theory, the polynomial depends on a q and a t. So t is k squared, right? So t is basically v inverse. So it's k squared. And if you look at the polynomial for 1, it really is a polynomial in k squared, right? So, and that k squared is t. So that's how it specializes to the Macdonald polynomial. But for higher n, you need to pick a square root of k. So q is the cube. T is k squared. And so the first one is the Macdonald polynomial, and then these other guys are some very interesting deformations of the Macdonald polynomial, which depend on these auxiliary, roughly g over 2 auxiliary parameters. So since I'm only going up to 5, I will have at most 2 parameters. And for the case 4, I have really just 1 parameter, and the second parameter is a sign epsilon. So for n equals 2 or something. So here there's just a sign epsilon. Okay. So far, G2 didn't show up. Now, let's look at the next set. So for 0, 1, 1, this is the Macdonald polynomial. And these guys look like you might almost understand because they look kind of similar to Macdonald polynomials. And here as well. Okay. So, all right. So here is the situation. There's not much going on here. And here, the Macdonald polynomial is kind of the most complicated, and these other guys are much simpler than that. And this is something that's true in general. There's a sense in which the terms of these metaplectic polynomials, if you write them this way, are contained in those of the Macdonald polynomials. And so my student Jason Sahi has given an argument for that. Here is the situation for 0 to 0. Okay, so here is the Macdonald polynomial. And these other guys are simpler, but now we see for the first time G2 appearing in here. Okay. And here's the story for 002. So Macdonald polynomial is kind of complicated, and these guys are, as I said, they're somewhat simpler. They have in general, in some stable limit, they have the same number of terms as the Macdonald polynomials, but they have at most as many terms, but the coefficients depend in some interesting way on the Weyl parameters. Okay, so that's all. Explain.
Thank you very much. So let's thank Siddhartha. Any questions?
I have a question.
Yes, hi.
Hi. So what about the symmetric Macdonald polynomials?
Yes. Yes, very good question, Philippe. So yes, you can define them, but they are not symmetric in the usual sense. They are symmetric for this deformed action of Chinta and Gunnells, for this complicated action.
Mm-hmm. I see. Okay.
Yes, because the Hecke algebra action kind of deforms that. So the usual Hecke algebra action, symmetric things are symmetric for the Weyl group. But here also, but now the Weyl group action was already pretty complicated to begin with.
Okay.
Nevertheless, there would be interesting things.
Other questions?
I know a representation of affine Hecke algebra which appears in Schur-Weyl business. Like it's a centralizer of affine quantum group in tensor product.
Sorry, so who is speaking? I cannot see.
My name is Roma Gonin.
Yes, yes. Okay, now I can see you.
Yeah. Okay. So I know a representation of affine Hecke algebra, which is centralizer of affine quantum group. If you take tensor product of several evaluation representations and
yes.
then consider.
Yes. So this is you're explaining you're explaining maybe Jimbo Miwa duality. Jimbo duality.
And is your representation of affine Hecke algebra this representation?
So first of all, so what you explained is really some type A story. So clearly not, because we have an arbitrary root system. But in type A, could there be some relation? Possibly, yes. So it's something like Schur-Weyl duality going on. And it would be interesting to understand that.
Okay.
In fact, what you explained is really a GLM theory, not even type A.
Okay.
Other questions?
Hi, I have a question. Hi,
yes.
Anna.
Hi, Anna. I cannot see you.
Oh, sorry. I can fix that, I think, relatively easily.
Yes,
sorry.
hi, how are you?
I wanted to ask, do you know, I mean, as I understand, you have sort of the corresponding metaplectic demonstralistic operators built out of this multi-parameter action. Right?
Yes. So when you say demesuralistic, probably you are referring to specializations of intertwiners. So we have intertwiners here.
Oh, I see. So
you understand how the intertwiners specialize to demesuralistic operators, and this is the connection between. This is how you get the connection between non-symmetric Macdonald polynomials and Whittaker functions.
Yeah. So that was going to be my question. If sort of
exactly. So that's right. So once you get the representation of the double affine Hecke algebra, you have intertwiners, and this is how one can make the connection with with these specializations.
Right. So in particular, do you know how to express these these metaplectic polynomials in terms of those operators?
Yes, yes,
So-
absolutely, absolutely. This is why there's some hope of having combinatorial formula, and Jason Said has, for type for GLN or something. You can see
I
how
see.
we can get alcove models and things like that.
Ah, I see. That's very exciting. Thank you.
You're welcome.
Other questions?
Representation of double affine Hecke algebra which you obtain, is it reducible?
Generically irreducible. So, but we can actually describe this, but this is work in progress. It's very interesting. We have it, and we're just, because it's so beautiful, we want to make sure that we present the best version. So we're already into some, I think, third generation proof, right, Vidya? Vidya is here. You should bear me out.
At some point in the abstract, you mentioned something about specialization of this GI parameters and Dirichlet sums. Could you say a little more about it?
Gauss sums.
Yeah, sorry. Yeah.
Not very much. I mean, so yeah, it's so okay. I mean, you can look at right. It's not too complicated. It involves some Hilbert symbol, but you should just look at, for example, work of Chinta and Gunnells, or I think also in Anna, the Chinta-Gunnells-Puska, as it's explained, right? Anna, you're here.
Sorry, the which one?
How do the GIs arise? I mean, what are the Gauss sums that the GI you have to? It's interesting to specialize the GIs.
Yeah. Yes, I mean they're sort of it's sort of relatively quick. Like it's just some usual Gauss sum, so it's not very hard.
Exactly.
They're there in Peter McNamara's papers. Yes.
And I also had an extremely poorly formulated question. By any chance, do you know of any relation between your work and this work of Gerasimov, Lebedev, and Ablezin, where they obtain some...
I'm sorry, I missed the names.
Gerasimov, Lebedev, and Ablezin. So they have these works where they obtain Mellon-Barnes times formulas for Q-Whittaker functions from certain Gelfand-Seyton representations of quantum groups. And
but these are ordinary Whittaker functions or metaplectic?
I had an impression that they had something about metaplectic as well, but I wouldn't bet my head on it.
Okay. I mean, if it's ordinary, then that's already that's sort of okay. So I don't know. Maybe you can have a model for them, but somehow the connection between non-symmetric Macdonald polynomials and usual Whittaker functions, it's known, and so something about these polynomials, the kind of some higher level extension of this theory. But since these polynomials have their own life, and some specialization is interesting.
There's an answer in chat from maybe you could actually say that out loud. Useful.
There is something in the chat. Oh,
yeah, there's an answer. Yeah.
How do I see?
So my understanding is that the work of Gerasimov and all is in the Archimedean case. So they study Whittaker functions over a group over R, for example, and Chinta and Gunnells work over periodic fields.
Yes, that's
so
right.
They're not a priori. You cannot equate them, but there are probably relations between the two.
Yeah. Right.
So, are there any other questions?
Excuse me, I have a short question. You said your polynomials generalize Whittaker functions. Are they spherical?
Sorry, again, who is talking?
This is Valentin Puciumaș.
Oh yeah. Oh hi.
University
Can
of
I see you, or can you?
Sorry, yeah, I can turn on the video, I guess.
Yes. Hi, how are you?
Hello. You mentioned your polynomials generalized Whittaker functions. Are they metaplectic Whittaker functions? Are they the spherical or the Ivahori ones?
The Ivahori ones. Well, of course,
ones,
the
okay.
spherical is a special case, some combination. But so I'm getting the ones that that should generalize the Ivahori Whittaker functions. Yes. And if you want to get the spherical, you have to choose. Well, you choose a It's a combination of Ivahori.
Okay, you add them up. Okay, thank you.
Yeah, I should have said Ivahori Whittaker functions.
Other questions? Okay, then thanks Siddhartha once again for the wonderful talk.
Thank you.
And
very nice to be able. I mean, this is like so good. This is so cool. I mean, I should have probably cleaned up my office a little bit before giving this one. But this is just so nice to be able to. We can work online, mathematicians.
Okay, thank you very much. Yes, sorry, please. Okay, so the slides are on the website, and the recording will probably also appear. So hope to see you next week as well. I think we're having a talk by Andrei Smirnov from Chapel Hill. Okay, thank you.
Bye.